Okay, Dr. Thank you very much. Yes, the talk I'm going to present today is joint work with several people. So I have an analysis part where this is joint work with Helmut Abels and Felicitas Bürger, who are both here in Regensburg, and it was the theme of the PhD thesis of Felicitas. So a lot of work you will find in her thesis. And I will also present a little bit on numerical results. This is together with Charlie Elliott and Balázs Kovács. We have heard quite a bit on the mean curvature flow, and let me review the equations. So this is a classical evolution law for hypersurfaces. Yeah, let's say you have a hypersurfaces in RD plus 1. You compute H, which is the mean curvature, and then you want to evolve this hypersurface in the normal direction with the velocity v, which equals this mean curvature. So these are the main players in this talk, the normal velocity v and the mean curvature h. So when you have given an initial hypersurface, gamma 0, then we would like to compute a family of hypersurfaces which are time dependent and which follow the law above. And the typical situation is that the enclosed volume decreases and the enclosed volume goes to 0, typically in infinite time. Yes, we see an example evolution down here where you have a donut type surface, and this shrinks to 0 enclosed volume in infinite time. So the mean curvature flow has a gradient flow property. This was also mentioned during this week. So again, v equals to h is the evolution law, and this is, can be understood as a L2 gradient flow of the area function. You just compute the function 1, you could say, on the surface. This gives the area. And you can easily compute by using some transport theorem that the time derivative of the total surface area can only decrease in time. Yeah? And I review some important properties of mean curvature flow. Yeah, so as we have seen, the surface typically shrinks, and the surface will go to let's say it's initially convex, it will go to a single point in infinite time. Yeah. We also know that convexity is conserved, and even further, mean convexity is conserved, and typically no self-intersections occur. So these properties are well known, and I would like to introduce a different flow, and then we will see what kind of properties will be also true for this other flow. So the situation I would like to look at now is the following. So we now have again hypersurface, let's say in RD plus 1, and so we assume no boundary. But now we consider a concentration, a function on the surface. Yeah, for example, here where it is dark, the concentration is high, and where it's lighter, the concentration is low. And we have in mind later on maybe physical applications where there's a concentration of the substance on this surface. And typically the total mass should be conserved of this quantity on the surface. So the integral of u, which is the surface concentration, should be fixed. And I have a new quantity, so this will also enter the energy now. As energy now, I take the integral of gamma of g of u, where g is a function, typically convex function, and now I would like to flow both gamma and u in such a way that the energy decreases. Yeah. So I would like to look at evolutions. Yeah, so now I have the gamma of t, which evolves, and the u of t, which is the quantity on the surface, which now also is time dependent, but it's time dependent on different domains of definitions because of the fact that the surface will change during the flow. But I would like to keep the mass, due to physical reason, to keep the total mass to be constant. Yeah. And so this is the energy, time dependent. And I now want to flow this also with a gradient flow, but I want to preserve the mass. So I cannot take L2 gradient flow with respect to U. So what do we do instead? Yeah. So we use an appropriate gradient flow for this energy E. So remember, you have the surface part and U, which is function on the surface, and we take an L2 gradient flow with respect to the surface gamma, and an H-1 gradient flow for the surface U. Yeah, the H-1 gradient flow, like you would do it, for example, for a Cantilever. Yeah. So what is let's call it state space. So the space of quantities in which we look at the evolution. So we have hypersurface and a concentration C. So the C should be defined on the hypersurface, and I have an index M here, which tells me that the total mass of C, so the integral of C over sigma, is given by this quantity M. So now I have to say what is, at least formally, what is the tangent space of the state space. So if I change the geometry, if I change the concentration, I can only do it in such a way that after this change, the concentration, the total concentration fulfills this law. So I can flow the surface with a normal velocity v. I can change the c to a c, let's say c plus delta times v, but the v needs to fulfill certain quantity, a certain identity, and that is the following. The integral of v minus c times mean curvature times v is equal to 0. Why this term? This comes from the transport theorem. Of course, if you change your surface, for example, if it increases, so the same mass has to be distributed more loosely because you have more surface area. Yeah, and this is basically what you see in this transport theorem. If you take the time derivative of u on these evolving surfaces, you get here the material derivative of u. You have to take a material derivative because you have to move a material point maybe with the surface, and you get this quantity u times h times the velocity. Yeah, and this is the reason why you see this constraint here, which is basically related to this fact that we fixed as a mass. Yeah. Okay. So what is the governing equation now? If I take the L2 gradient flow, then with respect to the surface, I get now that the normal velocity is given by a function of u times h, and the time derivative of u, let's say in the material time derivative of u, is given by the Laplacian of g prime of u. So the integrand was g of u. So I take the first variation. This gives g prime of u. But if I do it with in the h-1 topology, I have to also put in Laplacian here. And this basically comes from the term which we saw on the Reynolds theorem. If we do this, we get conservation of mass. So the total mass does not change in time. So you can use Reynolds, and this just gives the Laplacian. And we look at a closed surface, so we have no boundary. So Gauss tells me this is equal to 0. And we also get a reduction of energy. You can just compute the time derivative of g of u of t over gamma of t. And you see you have basically two dissipative mechanisms. One is given by is the velocity squared, and the other one is the gradient of g prime squared, which is like in a typical diffusion process. Okay, so this is a situation. Maybe we go back here. So if we just look at simple diffusion, where the surface is fixed, dt of u is equal to the Laplacian of u, let's say g is just a quadratic, then you get a diffusion equation on the surface, but also there a lot of things appear. For example, depending on the geometry, and the geometry now changes, maybe it is the diffusion process is quicker or slower depending also whether you have, for example, small necks. Yeah, because I mean, diffusion wants to make everything equal. I mean, everything should go to a constant. But if you have a thin neck, it takes time to diffuse through this neck. So this is one phenomenon which appears here also. Yeah. Okay, let me tell you the content. So I will study this evolution equation. I will first talk about short-time existence. Then I will look at properties of solutions. I will show a few computations, and if time, if I have time, I will tell you something about numerical analysis as well. Yeah. Okay. So one thing is something you quite often do here. So you give yourself a reference surface and you write the evolving surface as a graph over this reference surface. So this is probably well known to many of you. You have a point X on sigma, and then you move in the direction of the normal of this fixed surface with the distance r. Yeah, so this is what we do, and this we can now do time dependent. Yeah. So we have x plus rho of t of x times nu, and when we find this function rho, we know the evolving hypersurface. This we can do at least in the local neighborhood of the surface if the sigma is let's say C2. Yeah. So this is, but we will need more regularity later. Yeah. But this is what we do. Remember, first of all, we want to have a short time existence result, which but we will later, for this qualitative behavior, we will need certain properties quite in a quite detailed way. So we know we do the transformation on the reference surfaces. I said, by knowing this rho here, which is the distance function, I know the surface. Yeah. By moving into going into the direction of the normal, but then I also need to want to write down this PDE, which is here still defined on the evolving surface gamma. I want to define it on the fixed surface as well. So I do a pullback of the concentration. So theta rho is parameterizing the surface in a way, and then V is now living on the reference surface. So this is a PDE system which I have to solve now on the fixed surface sigma, but of course I get the evolution by computing this distance function. So let me look a little bit at this equation. So here H is the mean curvature, so it's a second order operator. Yeah. So I need second derivatives of rho to compute it. And you see here I need the second derivative squared. So it's a quite nonlinear term in this equation for V. So this will cause difficulties. Yeah. So what I do is, or what we do is splitting Ansatz. Yeah. So we first give ourselves a V. We compute a rho of V as a solution of this equation. Now we assume V be given. So this is like solving mean curvature flow, but now with, let's say, with an x-dependent forcing. So this one can do. And then I compute a solution V hat, yeah, on a given evolving surface where the surface is defined by rho. Yeah, so now I have an evolving hypersurface, and on this I compute the velocity. But due to the pullback, everything is done on sigma. But you see here still again some second derivative squared of rho appear. So this is a quite nonlinear equation. But both equations are now strongly coupled, but second order. Yeah. And the idea is you use now mappings. Yeah. So S, which defines a V to rho V, and then rho V goes to a V hat. And of course, what we want to show is we want to have a fixed point on this composition, and the idea is using a contraction mapping principle, and this you can do. Yeah, I stressed it before. This equation has this highly nonlinear term. To be able to deal with this, I mean, of course, you can also think of working in the Sobolev setting, but because we have this highly nonlinear term, we use the so-called little Hölder spaces, hk plus alpha to solve the equation. Let's say if you, because we did this splitting, we have two elliptic operators here, one with respect to the mean curvature, here with respect to the diffusive part, and we can use theory of analytic semigroups, linearize, and solve the linearized problem, and then of course there's some work doing the contraction argument, but this is possible. Here we need to be very careful. We want to have good dependencies on the geometry and on rho to show further qualitative behavior. Yeah. So the theorem is as follows. So we need a certain assumptions. So the g, this was g of u was a function we integrated on the surface. So this needs to be convex. We had this equation, normal velocity equals small g times mean curvature, because you want in front of the mean curvature operator, you want to have something positive to stay elliptic. So this is why we need an assumption that this small g is positive as well. And then in a setting of these little Holder spaces, assuming enough regularity, and we can show local existence. I mean, of course, first of all, for this PDE on the fixed reference surface, but then of course this defines in the evolving surfaces, and then the functions on the evolving surface. Yeah, so this is basically the background in PDE analysis for nonlinear semigroups, which you need. Now let me come to the qualitative properties, and here I always compare to mean curvature flow. And what I state now, due to time reasons, I will just show you what we show without what we can show without presenting precise theorems, but everything can be proved. Yeah, of course, here again the properties which we know from mean curvature flow. So we know things string, we know convexity is conserved, and there are no self-intersections. So the question now is this transferred to this new evolution law? So one computation which you can do, if you now integrate the one and not the g of u, then you see that you still get an inequality. Yeah, so the total surface area is also still decreasing under this flow. So everything has to shrink. Yeah. So this is the first observation we have. But let's look a little bit closer. Does it? Let's say, okay. Let's think of single of convex surfaces. For the mean curvature flow, they would shrink to a single point, or let's say they would converge to something which encloses a zero volume. Yeah, and this is not transferred to this new flow. Yeah, so you can show, depending on this function g, of course, that there exists a radial solution. Yeah, so r of t. Yeah, so in mean curvature flow you would get you would have a root light singularity at some point, but here you have situations where you find, let's say, space-independent functions u of t and spheres which collapse, but the radius of the spheres will only collapse to zero for t going to infinity. So this is drastically different to the mean curvature flow. We had mean curvature flow here, everything disappeared very quickly, but here we have to, of course, for the numerical isolation, we have to stop at some point, but this would go on for forever. Only for t going to infinity, the r would go to zero. Yeah, so this is one of the qualitative properties. Let's look at convexity. Yeah, is convexity conserved? Yeah, and here we have a disparate picture. So for curves, it is preserved, but for surfaces, it is not preserved. So what do we do? So we think of an axisymmetric situation. So think of this profile. and you rotate it around the x-axis, so you get let's say a sigma. And now if the concentration of the U is large here at the initial time, you can make the surface non-convex. But this is only for this you need this extra dimension. For curves it would stay convex. So this is a theorem. This we can prove. I have no time to state this precise, but to make this all precise, we need a very careful estimates in our local existence result. Yeah. So here you can also see the evolution. On the left, we saw mean curvature flow. Everything remained convex, but here we have a loss of convexity. Yeah. So this is one of the properties. But then here we see it again. But then we can also ask ourselves, what about mean convexity? I remind you what mean convexity means. Mean convexity means A is greater or equal to 0. Is this preserved when we have this at initial time? And the answer is yes, it is preserved. Yeah, and the reason is the following. So mean convexity is preserved if the mean curvature is greater or equal to 0 at initial time, it stays so. Yeah. And here the idea of the proof is it's similar to what you could do for mean curvature flow, but here things are a little bit more involved. We know that we can compute an evolution equation for the mean curvature, which is also very important when you study mean curvature flow. But here you have also this g function. But you know, you have a time derivative of the mean curvature, the rotation of the mean curvature. Here we have the gradient of the mean curvature, and here we have h as a factor on the 0 order term. And when you know about comparison principle, you know that this is enough to show that non-negativity is preserved. Of course, there are some technical details here, but this is the main argument behind. Yeah. Okay, so that is so mean convexity is not conserved. What about self-intersection? So for the usual mean curvature, let's say a surface, or in this case a curve, gets close to each other, then you always have the situation that the inner part needs to be, morally speaking, needs to be curved to larger extent, and has to move quicker. That's basically the reason. I mean, to make this precise, you also use a comparison principle. Yeah, but now here you can do the following thing. This outer part can have a concentration which makes this evolution quicker. So this you can draw these pictures very easily to make these things precise, really to control the velocity and show that really something intersects requires a lot of precise estimates, and here you have to very carefully look at the local existence theory. Yeah, and this you can also see here. So the evolution we had before was to the left, very close together, and the yellow bit here, and which you also see here, is the one which was moving through the blue surface. Yeah. So, but this can you also, this is a numerical computation done by my colleague here, Balázs Kovács, but this can be made precise also. Yeah. Okay. So here you see it again, and then we continue to summarize. Yeah. So we have convexity conserved in 1D, let's say, or for curves, for surfaces it's not conserved, and we can have a self-intersection, but also something which is maybe interesting. You can have evolutions which exist for all time without seeing any singularities on the way. So very shortly, I would tell you something about our numerical approach, because I like this a lot. So this was ideas of this are due to Kovács, Lee, and Lubich. So what they did was the following. So there were there's a lot of known about numerical computation of geometric evolution equations. So a lot of Gerd Juk, who was a pioneer in this case. Of course, you have level set method also, but we stick to the parametric approach. I did work with John Barrett and Robert Nürnberg, but there was an independent approach by Kovac, Lee, and Lubick. They used evolution. This is for mean curvature flow. Now they used evolution equations for the normal and the mean curvature to compute the geometry. Yeah. So what you have to do always, you move your surface with mean curvature in the normal direction. And when you want to do this, it's enough to know the normal and the mean curvature. So the idea here was you compute the normal, the mean curvature, and then you move with h times nu your surface. So this looks a little bit complicated, but when you do this, you get a lot of information, geometric information, and this can be used to numerical analysis because you have second order information and normal information into account. Yeah. The question is, does this approach also work in our context? Yeah, and it does. So following Huysken, or at least there we found it for the first time. So you have the following geometric identities. Yeah, so the gradient of the mean curvature equals to the Laplacian of the normal plus a here is now a squared is the square of the norm of the second fundamental form times the normal. So you have this identity. You have the time derivative of the normal equals the gradient of the normal velocity, and you have this identity. So these identities were behind the formulas on the slide before, and we can now also use these for this new evolution law: v equals g of u times h. Yeah, and you get, for example, for the normal, the time derivative of the normal is given by this right-hand side. So if you divide by g of u, you get a nice a quasi-linear structure with respect to the elliptic operator, and this can be used to discretize the equation. So altogether, what one does is the following. So the time derivative of x is given by a velocity, which is now a vector. The velocity is given by the normal velocity times nu, but how to compute them? They solve this system of PDEs. So time derivative of the normal equals something, time derivative of the velocity equals something, and now I have this abbreviation k of u and v is 1 over g of u times the velocity. And I have here an evolution equation, which is basically the one I had before for the concentration. And this leads to a natural algorithm, and we can also do a convergence analysis for this. I won't have much time to show you the details, but when you do what we do is a finite element approach. For this, of course, it's important to have a weak formulation. That's why I wanted to have the Laplace operator, for example, isolated to do integration by parts easily. So you get, for example, here, this is a weak formulation for the normal. Here I did one integration by parts. I get some junk term here on the right hand side. And there's also, using the transport theorem, a nice weak formulation for the concentration, yeah, which uses basically test functions which are transported with a velocity. So that's what we do here. So then we use an approach which is called the evolving surface finite element method, which is goes back to Juke and Elliott. We use subtle numerical analysis for surface PDEs. So Juke was a pioneer there, but also Demloff did a lot. And there's some. So for those of you who know finite elements, there you always have basis functions, let's say, which are 1 in one node and 0 in the other node. And the nice thing here is you get for this, you can now look at evolving basis functions, and they have a material time derivative which is equal to 0, and this greatly simplifies the method. Yeah. So I don't have much time, so I go through this rather quickly. So what we have in the end, so maybe I discuss this a little bit. So we have let's say a true surface gamma of x which evolves in time. So we interpolate this one, and then we have a computed surface, and we need to bound errors. And this is, there's a subtle way, this goes back to Lubich and Kovac, basically, which relates these surfaces and which helps you by doing basically energy type estimates to bound errors. But for this, it is important to have enough control about geometric quantities like a normal and mean curvature. Yeah, so this is also basically we need W1 infinity norms of the errors under control. But this can be done. Yeah, and what we have is here are the different quantities. X is let's say a position vector. V is a velocity vector. Nu is a normal velocity, and the U we get order k convergence with respect to these quantities. Here I should say this is an analysis of a semi-discrete method that we discretized in time, but sorry, discretized in space, but in time we are still continuous. Okay, let me sum up. So we derive new geometric evolution equation coupling mean curvature flow to diffusion on the surface. We showed well closeness. We analyzed the qualitative behavior. Loss of convexity is possible, at least when you have surfaces. For curves, this would be not the case, so curve would stay convex. We have preservation of mean convexity. Infinite time existence is possible, and we showed error estimates for the numerical scheme, which was also used to illustrate the results. Yeah, so there are many problems. What is the asymptotic behavior close to singular times? What happens for curves in the plane? Can we have, for example, we start with, maybe any curve, but let's say even starting with something convex. Do we get existence until shrinkage to a point? But obviously the shrinkage could be at infinite time as well. Yeah, but I would expect there would be no singularities in between, but we don't know. Yeah, and thus the concentration has enough time to go to the mean before the surface shrinks to a point, which would be the case for, let's say, on a fixed surface that you converge to the mean. Okay, that's all. Thank you for your attention.
Thank you, Harald, for your talk. I guess there are questions. I guess.
I have a question. May
yes,
I?
please.
I have a question to Harald. Well, in the beginning, you speak about conservation of mass.
Yes.
In your system, you have conservation of mass, right?
Yes, conservation of mass for this quantity which lives on the surface, yes.
Right. So when you write all the system, all the equations, I will expect some term related to a Lagrange multiplier of that constraint. I do not guess where that was, if it exists or not, this Lagrange, somehow kind of Lagrange multiplier of that constraint in the system.
No, there's no Lagrange multiplier because it's inherently kept by using an h-1 gradient flow. So that is like if you take a diffusion equation on a fixed surface, let's say, or let's say in a domain, and you take Neumann boundary condition, you also the total integral of U is conserved. This is similar here because we have the Laplacian of this G prime of U. Yeah. So if we integrate the Laplacian and we have no boundary, the integral of the Laplacian is equal to 0. So this is what it's basically, we go back, it's basically this, no, where was it? I have it somewhere. It's basically this identity. I have the time derivative of U, yeah, and then I have a transport theorem, yeah, which tells me this is a time derivative of U, but there's also a term coming from the change of the geometry. So if you have a precise, maybe I would put brackets here, yeah. But this term is also in here, and this gets subtracted. So this plus this is equal to a Laplacian, and integrating the Laplacian, I get a 0 because I have a closed surface. Yeah. This would be different. Let's say if I have a surface with boundary and if I specify directly.
Okay. Yeah. Okay. Thank you.
Thank you. I see two people asking, maybe Shahrukh, please ask a quick question.
Okay, Professor, so sorry, so it could be very stupid, but can you give some explicit example of G which satisfy your assumption?
Okay.
Apart from constant, let's say.
Yeah. So the G which I would need to take would be let's say a negative negative power of U. Yeah. So if you choose the power in the proper way, I don't know the exponent, but I think U to the -2, for example, does the job. I think.
Okay. So you can take 1 over U squared. I see.
Yeah.
Okay. I was thinking G is continuous. Okay, sorry. Thank you.
Okay. No. Okay, you would have yeah. But okay, because the concentration going to 0, it's concentration should be non-negative. So that's why let's say this state with U equal to 0. This would not be this would have infinite energy in this example. Yeah.